involved in this organizing the workshop. So without delaying much, let me start, and I'll be sharing my screen. So I don't think again I need to introduce myself, but still within few lines I'll just finish myself so that it would be a proper introduction of mine. Myself, Dr. Anvesh Kumar Nella, has pointed out by Sri Devi Madam, and currently I'm the assistant professor in VIT Bhopal University. So we are a good team in RF and microwave field who are working in the areas of planar antennas and then reconfigurable antennas for cognitive radio applications. And then we are also looking into some high directional ultra wideband antennas as well as terahertz antennas. And we too have scholars here at VIT Bhopal. And I have specially full-time scholars as well as part-time scholars, and they are working in RF energy harvesting. That is one domain where we are exploring currently. One scholar is working in RF energy harvesting, and then another scholar is working in plasmonic observers in visible light spectrum. And these are about full-time scholars. And then I too have part-time scholars who are working in 5G antennas. And another student is also working in 5G mobile communication. One more scholar, she is working in terahertz imaging. Currently, just she is about to finish her coursework, and then will be starting uh, original implementation of her research work. So just this is because I just want to whenever we discuss about write this platforms, then there is a great scope for collaboration. So in this regard, like I just introduced myself, and then I pointed out special areas where we are working, so that if there is some possibility of collaboration with this eminent researchers who have been participated in this event, then there would be a good win-win situation for this workshop. Okay. Apart from that, once again, let me clarify. Let me just ask one thing. Like, I am audible, right? Clearly.
Sir.
Okay. Thank you once again. With this, let me just say good morning to one and all. I'm just starting from just the basics of antenna, and it's my don't think that sir, like we're in good level, we do understand about antennas and all. But to make just a continuation from basic fundamental of antennas to whatever is my problem statement, like directional antennas for ultra wideband and terahertz applications. That is where I conclude. But I'll start from what is a simple antenna, and from there how infinitesimal dipole antenna works, how the radiation patterns are computed. So far we know that all might be using about HFSS and CST, or maybe some other softwares where they will be computing radiation patterns, S parameters, all those things, etc., etc. So in such case, how this software platform analyzes your antenna performance characteristics. That is what I just want to ensure that. Yeah. That is also I'll little touch upon it, and then later on I'll just go to my problem statement. Directional antennas for ultra wideband and terahertz. So as you know that antenna is a transducer, or we say metallic device, uh, that is simply converting your electrical signals to electromagnetic waves, and electromagnetic waves to electrical signal. This is the fundamental definition. Everybody knows that. And we too also know that every antenna dimensions, whatever the length or width we consider, it depends upon its frequency. So as you know, if you keep on increasing the frequency, then the dimensions of the antenna would decrease. That is a conventional procedure how we calculate the dimensions of an antenna. So, and thereafter, we have just about antenna. Then from there, like we have electromagnetic spectrum from radio frequencies to gamma rays. Again, I just need not to mention that, but to just cover this as a continuation, I'm just putting this in. Uh, so I was talking about plasmonic observers, which are like in this range. So this is invisible light spectrum. So we could able to uh, work on the plasmonic observers because believing that sunlight is available almost in our daytime. So like that can be used for RF energy harvesting. And then if you look into the applications, sorry, antenna types and all, we have olden days, we could see there are certain antennas in, radio station like FM radio. At least our uh, fathers and they could have heard this thing. And then we could also see this is a simple wire antenna. And then we can also see these antenna where like in police personnel or long back, just 15 years ago, we could have used certain mobile phones where they are having this kind of structure. So that is nothing but your helical antenna. And then this is again one of the very well known antenna on our roofs. In childhood, we could see. Nowadays, we could not see them because now everything is dish TV, parabolic reflector, etc., etc. So these are the a few different types of antennas. I just want to show you. Next, yes, if you come to certain, let's say, radar application or whatever, then in dish TV, then these kind of structures are what we could see on our bungalows, especially dish TV or whatever, different. And these are again on the right side, you have these are the antennas which are used in radar applications like telemetry, satellite tracking, controlling, etc., etc. So these are parabolic antennas. And then again, we know that there are, if you go just if you look around your building or whatever, then you could see big base stations. In that, like you'll find the different antennas. Like this is one antenna and this is another antenna. That is how different what we call this communication service providers like Airtel or Reliance Jio, they would be installing their towers and then they would be putting their antennas to cover uh, antenna signals. So those are the different types of antennas. And we can see here again horn antennas, especially these are used in GPR applications like ground penetrating radar applications. Horn antennas, they are high directional that we know already. We could study it in our antenna course. And I believe that all our scholars or who had done the basic antenna course, right? Tata Babu, sir? Sridevi, madam? Oh, can anyone please confirm me? Like, yeah.
Yes, yes,
So they are scholars or they have done antenna course, right?
yes, sir.
Oh, thank you. Thanks for the confirmation. And nowadays, we could see this planar technology, like everything is printed on a PCB. So you can call planar structures because day by day, our systems are becoming portable and compact. So there is no scope for big antennas like wire antennas, helical antennas, and all. So everything is printed like your smartphone or maybe your tab, laptop, etc., etc. In those cases, like we have to use the planar technology, and you also guys knows that. so many publications in IEEE's and in Springer, elsewhere, everywhere, those publications are going on related to planar antennas. And then there is little advanced technology like intelligent reflected surfaces, and then RAS, reconfigurable intelligent reflecting surfaces. Oh, that era is going on nowadays. Frequency selective surfaces, that is also going on. Just this summary, and it is always means what I believe that whenever you are talking about a particular antenna or on the content of antenna, then for me it is always interesting to start from a single wire antenna. Single wire, because we know that antenna, that's a two-wire structure, which is having, let's say, positive terminal and a negative terminal. And on the positive terminal, you will be giving some excitation, and then a negative terminal is grounded. But whenever you talk about two-wire structure, it is open-ended transmission line. Okay, that everybody knows that at one side of antenna will be applying the voltage source, whatever your frequency, like gigahertz frequency or megahertz frequency. And then at the end of the antenna structure, it would be open-ended. But before that, we should also understand that we always take plus and minus, that is two-wire structure. But why can't we there is again the concept of single wire antenna. We should also see that how a signal is radiated. Okay, because it is always important to understand that how an electrical signal is converted to electromagnetic wave. We do know that antenna, okay, will apply electrical signal. It gives us electromagnetic wave. But what is the reason behind the generation of the combination of electric and magnetic field? That we should understand. So how this electrical signal, whatever is being applied to antenna, is converted in the form of electric and magnetic fields. So that is where the antenna concept starts. So for that, I'm not going to any derivations or mathematical analysis because we have short of time, and I just want to show my works, whatever I have done so far after some time. But before that, I'll just start with single wire antenna. Yeah. So if you look at this structure, simple wire antenna, then you consider certain length and all, then it would be having certain current, then value, etc., etc. From there, what will happen the moment you apply a certain signal on it, then finally I'll just come to one conclusion that this is the final equation. Means there is a certain sort of a derivation, but being antenna engineers, everybody should understand one relation: diz by dt is equivalent to, let's say, uh, length into acceleration, and then this thing. Okay, so I could hear some noise. Can anyone mute, please? Okay, so we should always see what is the relation between time varying current and acceleration of electrons in the metals, because it is believed or it is proved that when there is a acceleration of charges, because we do also know that velocity is, acceleration means rate of change of velocity. When there is an acceleration, then it produces time varying currents. Okay. And in the same way, if you have been apply a time varying current, then there is a acceleration of charges in the metals. Now, this is the equation proved in the literature by the researchers that this creates your time varying current. So my point is, what I want to conclude here is that whenever you want to make electromagnetic radiation, you take any metal or whatever. If you want to make any electromagnetic radiation, then either you have to apply time varying current or whatever is the source, but there must be acceleration. So this is the fundamental and foremost concept of an antenna, how it radiates. Now from this it is very clear. Okay, if I want to produce electromagnetic waves, then I should have applied acceleration, means sorry, I should produce acceleration in the metal wire, else either I should apply time varying current. This is what where the single wire antenna tells us. Okay, then if you let's say many people have a question like, sir, why we need to apply only AC signal, and then why not we should apply DC signal to antenna? Many times this is also I had been facing such kind of question, and again, yes, answer we know, simple. This AC means time varying current, di by dt, but this is with uniform velocity, because the moment you say DC, then the charges are moving with uniform velocity. So acceleration is 0. This cannot produce electromagnetic waves, because straightforward, we have the relation. If you have acceleration, then that produces time varying currents, or if you have a time varying current, then it produces acceleration. But in this case of DC signal, whenever you are applying DC signal, then it clearly states, since acceleration is 0, then I don't produce electromagnetic waves. That is the problem with DC signal. But there is another chance where DC signal can also produce radiation. Okay, again, I'm just telling you that there is a chance that DC signal also produces electromagnetic radiation, but in such case, your metal needs to be, means metal wire or conductor, whatever you are having, it should have different structure. In this case, when it will produce radiation, means it needs to be curved structure, or it should have bend, or it should have discontinuation, or it needs to be truncated, or it needs to be terminated. So though I apply DC signal, but I want acceleration which leads to time varying current, that is only possible even though I apply DC signal. In such case, my wire, conducting wire, because we said antenna is a metal device, in such case, it needs to be either curved, bent, a discontinuous, terminated, or truncated. So this is the story of your single wire antenna. Okay, but many times like we have to operate at AC frequencies like megahertz, gigahertz, and all. So instead of applying DC, because that radiation is not that great, so that's why we apply directly straightforward AC signal and get the required electromagnetic wave. So that is where the concept of two-wire antenna comes into picture, because single wire antenna, it is having a problem because it is not that efficient radiator, or then the required output signal may not be the proper one. And then from there, I just want to we'll be going to two-wire antenna. Then yes, obviously two-wire antenna. Um, Again, yes, I should always uh, it is always important to understand how this, sorry, just let me go back. Initially, dipole antennas were introduced. Okay, initially dipole antennas were introduced, and you know that dipole elements are vertical to each other, like they are having there is an alignment of 180 degrees between that. But what is the reason for moving into this structure? Like why we did not try this kind of shape, or why we did not try this kind of two-wire antenna, or why not this kind of structures? Okay, so we should always see that why in case of dipole antennas we have two elements one to another. and there is a phase difference of like placing is 180 degrees between them. So we should see that. For that, I have little logic for that. First, we'll see simply a state wire where I just told like you have your 2-wire antenna structure like this. So one metal is placed like this and another metal is placed like this. And I don't know like how many of you guys know about this. In fact, it is in our fundamental and antenna concept. What is the problem in this structure is the problem in this structure is that whenever you are applying a cycle, let's say a positive of cycle, I'm just considering positive of cycle, then it is plus and it is minus. So your positive pulse goes here. Since it is inverted, then I'll consider only this dimension, like this is lambda by 2 curve, lambda by 2 curve. So if I consider a lambda by 2 wavelength, then in this case, current is one direction, and then in the negative wire, it is opposite direction. Okay, so if I consider one cycle, it is not always for complete cycle. I'm just talking about one particular case. I'm not talking about all the cases because there would be multiple possibilities. Sir, like this is one possibility, and then this is another possibility, and this is another possibility. This is another possibility. That I'm not talking about it. This is a signal, input signals you have. A different like in the same cycle there would be different combinations, but I just want to take one off cycle of this one in this duration, lambda by 2 duration. If I say, then current in the positive wire is, let's say, forward direction, and in the next wire, means negative wire, it is reverse direction. So if you consider Fleming law, then magnetic field produced in this direction, let's say clockwise, and then in this one is anti-clockwise. So I'm not going into detail. I just want to tell this is a mechanism, and then we can just see what is the kind of principle of Fleming left hand rule or right hand rule, and then magnetic fields are produced anti-clockwise, clockwise. I'm not going into detail. I'm not sure in the sense particularly like a left hand rule or right hand rule or clockwise, anti-clockwise. Here my intention is just to tell you that in case of 2-wire, if you are placing wires in this way, what is happening? Okay, so in such case, positive and negative, so this field cancel each other. Okay, because one is in clockwise and another one is anti-clockwise, so naturally, and we assume that the distance is very small. And the distance is very small, so field is completely cancelling each other. Then it leads to no radiation. Then what we did, researchers, what they have done, they have tried tapering kind of thing, and then they have little spacing, some spacing over between the elements. So then in this case, you'll find some radiation, not it is better than previous case, but not that great what we are expecting. Okay, so finally we had come to a conclusion that if I have a structure like this, if I place, this is okay, this is cable, that's okay. This is where my antenna, and then whenever I do like this, then it is believed that, oh, finally it is up to the radiation what we are expecting. So this is what the story of 2-wire antenna, and then from there dipole antennas, then you have patch antennas, then many antennas are being produced from the concept of this simple fundamental monopole 2-wire and single wire and dipole antennas. And again, we should always see in case of dipole study, because your antenna like patch antennas or whatever the antennas would be analyzed based upon this fundamental dipole antennas only, means mathematical analysis related to your radiation pattern, or gain parameter, directivity, all those things will analyzed on the basis of dipole structures only. That is also I'll introduce slightly after this one. So this is about two-wire antenna. I think I should, yeah, yes. So in this regard, I just want to ask, like, if you have any questions, because this is one part of my discussion, then I'll go to some other discussion. Before that, if you have any questions in this regard, one question or two questions I can take up related to single wire and two wire. If you have any question, quickly, so that we can continue.
No, sir.
Okay, it's fine, fine. So then, again, yes, again, interesting discussion in antennas is how the these solvers work. For example, if you talk about HFSS, then it is based upon your finite element. Sorry, HFSS. Then it is like finite element FEM, and then you have FICO also, which is FTDD, like differential based upon differential equations. And then you have CST also, and it will also work on some other algorithms. And we should also see, like, what is the idea, basic idea in these algorithms. What is the how these algorithms, like whatever the softwares we have, how they have been used for simulating any random structure or any structure. So for that, the basic or the simple, the foundation starts with the infinitesimal dipole antenna. Okay, so in computing radiation patterns for any such kind of antennas and all, it starts with the infinitesimal dipole antenna whose length is very, very small. It is in the order of lambda by 50. Okay, if I'm not wrong, yes, whose length is very, very smaller than lambda. So it is around, like, approximately lambda by 50. And sir, if you ask me, like, why we need to study, because, for example, let me tell you now itself, so that it would be a clear understanding for everyone. If I'm having a big antenna, like let's say patch antenna or whatever is antenna, let us assume that you have designed this structure in HFSS, and then you are asking its S parameters, etc., etc. Now the point is, this fields needs to be computed. Okay, this field, each and every portion, whatever is it is trying to contribute, then its performance needs to be calculated. In this case, what they will do is, this complete structure is divided into multiple infinitesimal concepts. Okay, so this is one infinitesimal dipole, this is another, this is another, this is another, this is another. Like this, this total structure is divided into multiple infinitesimal dipole, so that the overall performance would be the summation of all these components. Okay, so you just divide the structure in row wise and then column wise, extra. Then at the end, if you sum up all these performances, like strength, whatever the signal strength you are getting, ultimately signal strength is nothing but your electric field, E theta and H pi. Don't think that, sir, why you are writing only E theta and H pi, though you have R theta pi, which are your spherical coordinates. Okay, r theta pi, which you are having spherical coordinates. In that, dominant fields are E theta and H pi. So ultimately, our target is to compute E theta and H pi for any structure. So whether you are HFSS or CST or FICO, whatever we have, everywhere the electric field and the magnetic fields are computed, that too E theta and H pi. Now the thing is, first you had computed for one infinitesimal dipole antenna, then that algorithm, whatever the algorithm in the software, it will compute like one by one, one infinite small dipole, then another, and then it will also consider mutual effects and all these things would be considered. That is how certain antennas takes 2 hours to simulate or 1 hour to simulate. And if you are taking very big problem statements like um, in defense radars, like it is here that they take 24 hours, 48 hours. So such kind of time they will take for simulation. Even I do run certain simulations. They will take 4 hours, 5 hours. Sometimes it will take half day. So such kind of problem statements are going on with us. Okay. Sometimes it may also happen that you give wrong settings in simulator. For example, you define dimensions in mm, and then use operating frequency, you give terahertz, then meshes will be calculated based upon your operating frequency. Suppose you have a structure, let's say in mm, let's say 40 mm by 30 mm structure. And then in this case, what you did, you have put your operating frequency in terahertz. So now in this case, your mesh size would be based upon this terahertz frequency. So if you consider this structure, then billions of meshes would be formed. So in that case, your system cannot able to run it due to RAM, hardware, processor restrictions, because that mesh will not be able to stored in the RAM, so it cannot be computed. So finally, the story comes is that the fundamental analysis should start from infinite small dipole, since all those antennas, all the antennas are analyzed based upon infinite small dipole. Okay, so we have a little, it is a great discussion. If it is theoretical class, then I could have mentioned each and every step one by one. But here it is very difficult. So let us consider a simple infinite small dipole antenna whose dimensions, as I said, like very small, approximately in lambda by 50. And here length is almost negligible. Okay, the infinite small dipole antenna whose length is almost negligible. In such case, like we'll do certain, from Biot-Savart's law. There is something called Biot-Savart's law in electromagnetic fields. Again, I'm not going into detail, but I just want to tell that it gives you a relation between magnetic field and I. Simple. Guys, one point I would like to tell here. Don't think that sir, your problem statement is directional antennas. We had just eager to hear. That's okay. That is just based upon some simulations and all. But because here we have a great community, good community, almost all researchers. So I thought like if I cover these concepts, at least few people will be exploring, and then they will be passing this knowledge to the next generation. Because in this there may be many teachers and professors and all. Then again in our UG level, etc., we may not be studying mathematics into that great related to antenna. But being researchers or professors and faculty, I believe that we should know about these fundamentals, so that at least we don't forget how an antenna radiates, then how the things are computed. For that only, I just had prepared myself to give you this knowledge. Okay, simple. Like there is something called Biot-Savart's law. What it says, like ultimately you have a wire, whatever the metal you have. So it will have current because we'll apply some voltage, and then it will have some current. Now, Biot-Savart's law states that at a distance d from the antenna, let's say this is antenna, dipole antenna, or whatever the antenna, and you had applied certain signal, AC signal and all. And then what it says that at a certain distance d, then there is a magnetic field introduced. That is what the Biot-Savart's law states. So you have certain element there at a distance, and this point and this point are not connected. Like this is your observation point, and then this is your metal antenna, and then we had a distance separation. Now during the application of your current in the wire, then it will obviously produce electric fields and magnetic fields, because you are applying time varying current means it is having electromagnetic nature, means electric field variation and magnetic field variation, both variations you have. Okay. From there, from the Biot-Savart's law, then you have a principle called magnetic vector potential A. We know that B equals to del cross A, and this is your magnetic field uh, density B, which is magnetic field density, and you to have another relation del cross A, curl of magnetic vector potential A, and this is one of the famous equation for magnetic vector potential. How we got that is different story, but this is the A from current whatever you are applying. Remaining parameters you forget about all these things and you need not to look into it, but you should only just know that A magnetic field magnetic vector potential is dependent upon current applied. Okay, this is, let's say, integration and all. So whatever the current we have applied, that is leading to magnetic vector potential. From there we'll get B, means magnetic field density. So this is just a proof that how you got this equation A equals to this thing. And this is Biot-Savart's law. Biot-Savart's law stays like H and I are directly proportional. This is the Biot-Savart's law. From there we get A, and here my A magnetic vector potential and current are what we call dependent. Okay, applied current I and induced, I should say, at certain point. This is a point where the magnetic field produced at the point, and this is applied. This is applied current. You see here, this is my metal, and I applied current I, and then from there here you have magnetic field. So once you get this magnetic field, then you can compute A, like there would be conversion from cylindrical to Cartesian to spherical coordinates, extra. So finally, I just want to say again, once you get B, I got B, and from there, like I have a relation E equals to del cross E equals to what we have is minus dou B by dou T. We know that Faraday's law, electric field Faraday's law for electric fields, del cross E equals to minus dou B by dou T. So in such case, like I can obtain remaining E from B, I'll get H, and from this relation, I'll get my electric field. So this is how the case for single infinitesimal dipole. This is for single infinitesimal dipole. Now, if you consider a big, let's say, complete full dipole, not full dipole, like half wave dipole, in the etc., then this summation would be considered. For example, if I have this half wave dipole, then this is one infinite, second infinite, third, fourth, 5, 6, 7. Like this, it would be divided into multiple infinitesimal dipole. Then finally, the final H pi is sum of individual infinitesimal dipole. So that is what the simulators will do. So simulators are not going to do some magic. It is based upon some mathematical study what we have missed during our study. So to just recollect or to just give you some insight in this case, this is the discussion I just have. I'm just telling it. So after infinitesimal dipole, you have many other designs also, like finite dipole, that small dipole, or many other dipoles you have. But again, for that also, the main fundamental design is infinitesimal dipole. So this is again. So finally, you will be calculating power density of this particular structure. Like you got E and H. E and H you have from E and H. you will be calculating power, how much power is produced. So ultimately what we want, power, how much power an antenna radiates. So that is what we have computed using the simple mathematics. So this is another layer of my discussion. So any questions, maybe you can ask, otherwise I'll continue further. So again, I'm sure ki, for so many students, so many scholars and all, it creates question mark. I'm sure this discussion, whatever we have made, I have made here, it will create question mark you to rethink about the antenna fundamentals. I may be sure, I'm not sure, but I feel like that. Anyway, whatever is the point, but I just want you to ask questions if you have any. Yes, please, if you have any questions. Any questions? Okay. I think there are no questions.
Hello.
Yes, yes.
Good morning,
please.
sir.
Yes, good morning.
Sir, what is the diversity of antennas, sir? Diversity
See,
or diversity?
there are diversity means variation. We say
Okay.
polarization diversity, polarization variation. Okay, perpendicular or
Okay, sir.
Parallel or difference. Actually, it is nothing but diversity means different. That's all. It is, if you look at see, I don't need to tell you that if it is antenna concept and all, we should think in another direction. No, if you look at simple dictionary meaning of diversity, that is what applicable to antenna diversity also. For example, polarization diversity. Diverse, we say a diverse, diverse. Yeah, that is what we generally use, diverse or diverse components, something like that. That is the same meaning we have, nothing else actually.
Diversity
point,
gain,
right?
diversity gain also, sir.
Uh-huh.
Diversity gain.
That is what diversity, it is having its own meaning. So if you say different gains, a polarization diversity means the how these antennas are oriented. In case of MIMO, we say polarization diversity because one antenna radiates in one direction and another antenna radiates in another direction. Let me tell you, we have developed some MIMO structures. What we did is, like, one antenna would be like this and then another antenna would be like this, then we'll adapt like this. Because now you see here, this is its alignment is in one direction. Let's say this is my x plane, x axis, this is y axis, and then let's say this is z axis. Now this antenna orientation is towards your y direction, and then this is negative y, and then this is in negative x direction. So obviously their polarization is also diverse.
Okay, sir. Okay, sir.
Okay, now they are
Okay, thank you.
perpendicular. They are like 90 degrees onto one another. So obviously it is like 90 degree polarization diversity, right?
Okay, sir. Okay, sir.
Okay, so any more questions? In this, especially, I would be happy if I get any questions in single wire and two wires.
Light
Yeah, please.
time the change ఉందంట.
I did not get, please. Okay. So then I'll just introduce next this thing, like whatever I supposed to discuss. Yes, yes.
Hello,
Yes, please.
sir. Regarding far field and near field, what's the current distribution of an antenna, sir?
Far field and near field.
Yes.
What do you mean by current distribution?
Yes, sir. From
See,
the antenna.
basically, the point is antenna is not in far field. I mean to say that antenna is in its location only, right?
Yes.
So then whatever like you apply, for example, let's say if you consider infinite small dipole, then current is assumed to be constant I naught, which is fixed throughout the length because its length is very small. So whatever the current you have, it is assumed to be constant, right? Now, if you take a small dipole, then what will happen? Since its length is little bigger, then it may have triangular pattern. Means at center it is maximum and at edges it is minimum. Okay, so if you just give me little time, then I can show you where. 1 second, please. So if you see here, in case of infinitesimal dipole antenna, the current is assumed to be constant fixed for infinitesimal dipole. So this is fixed constant since the length of the antenna is small. Next, if you go for finite, another one, small dipole antenna, it follows a current distribution of like this pattern. Means here at this center point, you will find maximum and then it is minimum at the edges. So this is for small dipole. And then you to have another structure, let's say finite length dipole. Then if you consider finite length dipole whose L is approximately lambda, then it is having this kind of current distribution. So this is the nature of current distribution is like this. So whether it is current distribution does not depend upon how far it depends upon what kind of current you are applying. It does not depend like on the near field or far field. The radiation pattern.
టైమింగ్స్ చేంజ్ ఉంటుందన్నారని ప్రొడిక్షన్.
The radiation pattern depends upon near field and far field. But if you talk about current, it is a internal parameter of a structure. So it depends upon only what kind of current you are applying and what is the dimensions of an antenna. I hope I have answered your question.
Okay. Yes, sir. Okay.
Is it okay?
Yes, sir. Yes, sir. Okay.
Okay. And you may be asking, maybe like in simulators, we'll be having some current distributions and all. So again, they're also same thing because we don't study mostly mathematics in an antenna structure while designing it. But fundamentally, if you talk about this is the reason, this is the concept. Yes. Any more question? Last 1 or 2 questions we can take and then we may take little break because I'll be starting the next discussion. For that, we'll have just a 5 to 10 minutes break. Any 1 or 2 questions in this regard? Single wire and then 2 wire or maybe then infinitesimal dipole mathematics. Yes. Okay. Okay. Okay, then I'll just continue the discussion. Maybe around 11:15 we may take a break then. Okay, so then let me start. Yeah, you may be waiting for this discussion. In fact, the problem statement which I had given to this presentation is directional planar antennas for ultra wideband and terahertz technology. Sir, yes, sir, we could hear about directional antennas. And we to know about ultra wideband and then we to know about terahertz technology. Sir, what we are going to see something new. Yes, see, I already said like these are the works that is what we and our team has done. So I'll just I'll just show what the different works we have done as compared to literature because it won't be uniqueness if I just discuss about what is the designs we have studied in the literature. I'll just cover them. These are the so far directional antennas, and then later on we'll see what additional techniques we had introduced complete novel technique introduced to obtain a directional antenna. And again, I need not to tell you guys about this what is ultra wideband because we know that ultra wideband is 3.1 to 10.6 gigahertz, which is unlicensed by FCC for unlicensed spectrum uses, because it is still under trials and then people are working in this research for
Hello, sir.
many applications like
Hello.
small wireless devices or all those things and all. Yeah, is someone calling? Okay, next. So FCC, based upon its interest by considering the frequency range, applications, advantages, they have just unlicensed this frequency 3.1 to 10.6 gigahertz. From there, that was around 2002. From there, people are publishing ultra wideband antennas, planar monopole antennas, partial ground, DGS, and then there is plenty of research articles in this, like last 15 years. So many IEEE transactions, then patents, novel techniques, and etc. etc. So means that the interest of researchers is also increasing. And then here my interest also, obviously, if everybody are putting their interest, then I am also part of them. So I too had spent little time in working towards ultra wideband antennas. So at the initial phase of my PhD, then I'll just simply simple planar ultra wideband antennas I have designed. But later on, once I little what we call means saturation. So we could publish certain papers in conferences, SCI. Then from there we felt, okay, this is done now, saturated. Now what else is to be taught? So that is where I have thought of directional antennas for ultra wideband. So that is what if you look at this directional pattern, this is the outcome of our teamwork only. Like this is again ultra wideband frequency. This is, I guess, around 10 gigahertz, and you can at least see that you have directional pattern. And it is not that easy, guys. Believe me, it is not that easy to obtain directional pattern to planar antennas. Yes, we know. Yes, we know. In the literature, there are so many articles, like I'll just introduce, but just telling, like you have Vivaldi antennas, then planar Yagi antennas, then uh, we have certain other planar structures also, where they would be producing a directional pattern. But here my interest is to come up with my own technique to make a directional antenna. My interest is that I don't want to look into the techniques of others who have used, or I just want to look into this works, because I just want to have my own uniqueness. So for that is what the work has been carried out. So yes, in this case, first I'll talk about ultra wideband antennas, directional antennas. So we know that the frequency range from 3.1 to 10.6 is very popular because it is having several advantages like high resolution, high data rate, and then it is said to be like it will produce 200 Mbps speed. Okay, in general, like this technology, ultra wideband technology, it is believed that it provide 200 Mbps speed at a distance of 10 meters. Okay, so that's why like there is a good interest in this regard. And many countries, like they have been using, it is not like all the countries are using from 3.1 to 10.6. No, in India, still, like we did not adapt any thing related to ultra wideband, at least in market. Still, like everything is under research. I should not comment over it because we too don't know like what exactly is happening at IITs, IISc, then extra NITs and all. But in the market, like nothing is like coming, nothing is available. So if you look at about the little literature about ultra wideband antennas, sorry, directional antennas, and we could see helical antennas. So this is one of the helical antenna where you have, and then you have Vivaldi antennas. And then you have certain log periodic antennas also. You have also Yagi-Uda antennas for directional antennas. But the problem with these structures is that you cannot fit them into portable structures. For example, mobile phones, and then any small gadgets like your smartphone or maybe your smart device, etc., etc. In such cases, we cannot able to uh, adjust these structures since they are in bulky, and then they are having dimensions issues also. So you may think that sir, Vivaldi antennas also suitable, but the main problem with Vivaldi is that they are having bigger in size actually. Yes, they are very good in providing directional performance, but the main problem with them is dimensions issue. Directionality is good, but the dimensions are good, very in bigger in size. So what we did is I had come up with my own structure after, let's say, I guess 3 to 4 months. I spent certain time uh, without having any, I could see I have studied what we call, I have studied the techniques of directional pattern, but I just had certain doubt that I should try this structure, then it should results to directional antennas. So that is around somewhere else 4 to 6 months. I could spend little time. From there, I could come up with this structure. So if you see, it looks like derived from planar Yagi-Uda antenna. It is having multiple combinations, I should say. For example, it is having flaring structures. At the corners, it is having flares. Next, it is having director elements on the top plane and ground plane. You can see this is top plane and this is your ground plane. And it is also having a partial ground with the certain ground slot. And then it is also having some L-shaped strip on the radiating patch. So it uses this antenna structure uses multiple techniques. One is like we know popularly that first of all partial ground. We know that it is used for ultra wideband characteristics. That is one thing. Next, you two also have slot insertion technique in the ground. So I have introduced a small slot. Better I should show here. Here you could see this is a fabricated structure. So in this case, you have slot, ground slot. This is also results to wideband performance. Okay, so this slot and partial grounds, these are two helpful in applying in getting the ultra wideband performance. Next, I need not to say these directors, they are used for what we call directional performance. The name itself says they are directors, but I just added directors on the top and bottom plane so that I have feeling that it will enhance my directivity. That's okay. It has worked. And then you two also have flaring structures. Yes, obviously we know that in case of Vivaldi, what will happen, like whenever you have center element, then at this corners you will be having different radiation pattern. Sorry, at this corners you have flares so that your antenna radiation would be put up in this particular direction. So by considering that, I too had put flares in this case. Next, you can see another slot basically here. This slot is mainly used for shifting the lower cutoff frequency, because many of the times we see you have inserted some slits or slots on the radiating patch, then it leads to a cutoff frequency shift from higher to lower, because the main reason in this regard is that for the current, it is taking longer path. So I should say, for example, let me just take a little one second. Here is because this is, I just want to show you so that you will understand why I have been used. See, the reason is that when you have a simple structure, like you have, this is my planar monopole, and then you have this one. Once current is introduced, it will directly go like this. It means, okay, current has gone. Let's say it has faced length L. Now, but whenever it comes to this structure, let's say current is going in this one, then again it comes down and again it goes back. It means what has happened? This is a total length has been increased. Okay. Physically, it is having this radius only, but what has happened? By inserting the slot, this current has to move for longer distance. So ultimately, if the current is moving longer distance, means length is also increased, then your resonant frequency go down lower side. So that is a reason. That is what I put that particular slot. So many times we design ultra wideband antennas with notch elements. So by putting the notches on this radiating patch, you could able to find shift in resonant that is cutoff frequency. I should say lower cutoff frequency. It will go down by considering that it is being inserted. Okay. So next, again, I just want to mention what is this simulation results, etc., etc. So here you have S11, like again, as I said, it is ultra wideband characteristics. Then it is below 3.1 to 10.6, and then if you look at simulated and measured results, that's okay. They are in good agreement. Again, then if you look at peak gain versus frequency, then initially, since it's an ultra wideband structure, many a times you might have observed that gain will increase like this. Means at minimum point at lower frequencies, you will be having less gain, and if you keep on increasing, then your direction of performance will also increase. And in this case, I was getting very good gain characteristics at higher frequencies. Okay, so though it is a directional antenna, but directivity is better at higher frequencies. That's why I could able to get better gains. I could get 10 dBi around with a simple dimensions like almost 40 by 48. It's a very compact structure. You see here 40 by 40 and then getting a gain of 10 dBi, the two directional performance. It's a good behavior. So then if you look at the same structure for the same whatever the proposed structure, I'll say that at 6.3 gigahertz, this is your directional performance. It is not that great, but okay, it's like directional performance, and it is having 6.5 dBi. Its gain is 6.5 dBi. And if you consider about 10.5 gigahertz, then it is having good directional performance. So this is about the structure. And here I just want to take just a 5 to 10 minutes break because it's around 1 hour. So we may have little like someone may drink water, etc., etc. So I'll just give little break for 5 to 10 minutes if this committee approves.
Sure, sir. Sure, sir. We'll have a break for 10 minutes.
Okay, ma'am. Thank you very much. It is 11:12, so around 11:20 we'll meet actually.
Okay, sir.
So shall we start or shall we wait, sir? Okay. Sridevi ma'am,
Sir.
shall we start?
Yes, sir. Sir.
Okay.
Yes, ma'am. Yes, sir, you can start.
Yes. Just to have continuation for that, I was just stopped where the antenna have produced directional performance. Now, if you look at just though it is like directional antenna, but since it is an ultra wideband, so you cannot what we call like say that it would lead to complete directional performance over the ultra wideband, then it is like a magic or wonder, I should say, because such kind of antennas, I mean to say that it is quite difficult, but it is not impossible. It's not like impossible, it is possible. So, but in our work, we could able to get like good radiation patterns at higher frequencies, like more than 6 and all. So just to show you the process, like what is the step-by-step process involved in it, I just trying to show you. Like this is simple planar monopole structure where everybody knows that like it's a simple planar monopole and then it's a partial ground, and that there would be certain calculation of it, like resonant frequency, lower cutoff frequency for certain uh, frequency and dimensions. So there is a standard relations by several articles, like what is the relation between this lower cutoff frequency and then this partial ground feed gap, etc., etc. That is also have been discussed in many articles. So now for this one, like it is the S11 characteristics, like you have. So here somewhere else, like it is missed. Here it is missed. That's okay, because I just have to enhance the uh, bandwidth, like S11 performance, which I supposed to enhance it. For that, in the next step, what I did is I just added a slot. I just mentioned earlier that by inserting certain small slot on the ground plane, it leads to ultra wideband performance. Now the results are in front of you, like we can verify that. See, earlier it is missing and this 2 bands, but here you can see by applying this, we could able to get the performance. So it means it is very well proved that by applying this slot on the ground plane, the bandwidth, impedance bandwidth, I should say, S11 performance, it has been increased. So next, then I had a feeling that okay, by putting it center feed, like this is what we call center, uh, it has happened that it is not at all giving radiation pattern, directional radiation pattern. If you look at this graph, then you can see like corresponding to this one and corresponding to this one, it is not directional pattern. Since it is a planar monopole, it leads to omnidirectional pattern. So it is very well known for us, like for ultra wideband antennas, that two planar structures will get omnidirectional radiation pattern. But what is my requirement? I should make directional antenna. So in this case, after thinking multiple attempts, like and after trialing many structures, and then I had also thought that like if you try offset feed, then what will happen? Okay, I had a feeling that if I go with offset feed like this, take your structure to take your feed line to at the corners of the structure, then what will happen? And at the same time, I should shift this slot on the ground plane under the feed line, because I can only get the wideband characteristics when this slot is being inserted under the on the ground plane of feed line. That is only possible to obtain a proper impedance bandwidth. Now, after looking into this, after considering into offset feed, Now let us see my radiation pattern. Okay, so second, it's like little glitch. Okay, anyway, like if you look at this one, you could see a directional performance corresponding to this thing. So this line, offset feed monopole, and this line, it leads to directional performance in one plane. So I would say little that, okay, by considering the offset feed, it is producing me a directional radiation pattern, and it is not that great directional performance, though the radiation is put towards directional, but to obtain proper directional radiation performance over the wide band, then we could try this flaring structures, whatever I have shown, like these flaring structures, and then director elements, extra, extra. Though finally all leads to this performance. Okay. So this is what now you can see here. So if you look at these two lines, double dotted and then a solid line, then it leads to a perfect directional pattern in both planes. Now this is about your XZ plane and YZ plane. So obtaining a radiation pattern in the one direction, one plane, it is possible, but we should also maintain directionality in all the planes, like XZ plane, YZ plane also. That is what the requirement. Then I was, it's okay. Like we had tried then multiple combinations of different techniques, like you have partial ground technique and then directional performance technique like offset field. From there, we can, what I can conclude is that if you apply offset feed, then it is possible. See, again, we have also tried the same thing for other structure also, like for planar structure also. Then it is also leading to directional performance. I think we do have this work was published in IEEE Access recently. It is 300 gigahertz actually. So it is also again based upon offset feed only, but you have some other interesting element there. If possible, I'll show that paper also, so that it is a guarantee or it is sure that by applying offset feed, you will get the directional performance. That is what I just want to confirm. Okay. Next, like again, this is again proposed structure radiation pattern at different frequencies. Like you see here, this line especially. One second. This line, it's a exam, like it is very narrow and then highly directional. So again, these lines are little zigzag, but if required, then I'll share this publications also, so that there would be a follow-up of on the word. So finally, I would say this is how what we tried for directional performance, and then our team succeeded in getting the directional performance using offset feed technique and then flare structure. So again, one more point I should say that flaring structures just enhancing the directivity, but they are not compulsory for your directional performance. Offset feed, it's okay, fine. So to show you to give you more clarity on it, then I'll show other that work also. Next, again, we had also attempted one more work on terahertz directional antennas, because nowadays people are focusing much on this directional, terahertz antennas, etc., etc. In this case, terahertz requires directional antennas. Let's say your automatic cars, or maybe your wireless devices, or home automation devices, etc., etc. In such cases, we need directional performance, and because our intention is not to make omnidirectional, because for example, in automatic cars, for example, you have a car and then you have to just have to see then in this case we want our antenna to radiate radiation pattern in directional. So that is what like our intention was to come up with those kind of directional antennas. Though it is like derived from traditional, like if you see, it is a combination of two antennas again. It is including bow tie antenna, bow tie structure we have, and then planar Aggie. As we know that directors will enhance your directivity, that's okay. But especially we had just come up with symmetric ground, like you have structure on ground plane as well as in the this thing. If you look at here, this is your top layer and this is your bottom layer. And generally, when you say bow tie structure, then people use like like this. But what we had in idea, like in order to obtain directional performance, how this structure needs to be modified, because bow tie will not give you a directional pattern. That is not its nature. But what I want is that I have to use certain technique on this bow tie structure so that it results to directional performance. So in this case, like we had tried with a step-by-step process, then finally we could succeed. I think I have the steps also. But before that, let me just show you the structure. This is a bow tie top plane and this is bottom plane. And this is what acting like a reflector, though it is on the ground plane, because in case of directional antenna, definitely there must be a reflector which can support you to make your radiation pattern in forward direction. So that is what the ground plane. And then symmetric structure on the ground plane is also used to balance the radiation pattern, because if you don't consider this one, it is not possible to get the directional performance. In order to balance the directional performance, you just have to use symmetric structures on the top plane and ground plane. So finally, if you see, then okay, it's fine. This is like HFSS and CST. There is a good understanding or no approach like same. And then you can also see this is just a comparison without directors and with directors. And then the solid line clearly tells like by putting directors on this planar structure, then it is enhancing your what we call directional performance. So at the higher frequencies, like in these frequencies, my directional performance is increased. So then have a look at like this is what the single element directional pattern we have. And then I could get the maximum radiation, gain of 10.4 dBi, which is quite good for the structure. And then again, let me show you just the understanding what exactly happened. This is structure initial step, but this is with full ground. Naturally, everybody knows that when you have used a full ground, then you will get a radiation pattern which is normal to the plane. Okay, for example, your antenna is lying in XY plane. Now, since you have a full ground, total signal is reflected from the ground plane and it will go to normal side of your plane. So that's what you will find all radiation in Z direction. Here you could see complete radiation pattern is towards Z direction. So then naturally, what I need to do now, I need to reduce the ground plane. Reduce the ground plane means in order to make the directional performance, I just need to consider the partial ground. The result is here, like you consider partial ground. The structure is same, like top layer is like that only. Then I had inserted a structure, partial ground structure. Then you see here, this is maximum towards Z direction now, but in this case, maximum towards Y direction. So from this, I can clearly tell you that I could achieve directional performance using my partial ground technique. Okay, so far we could see that partial ground is used for ultra wideband performance, etc., etc. But there is also possible that if you consider small ground plane, see, this is as small as compared to this length. Okay, if you consider the length of this structure, then maybe by 2 means half of this one, or below that also possible to have the ground plane. In this case, I'm just getting directional performance. Then in this work, I just show this research article because I did not include it in this this thing slides. So if you could see this thing, first to okay, let me just take marker. Right, just one second. Right, so I'm just considering this structure. This is the first step, and then this is the second step where you have the partial ground. From partial ground, you could see that it is able to give you directional performance. That is what I might have here. You can see here, like this is the directional performance. And next, in the third case, what we did is just to attain proper frequency, because we were interested to develop at 300.
Hello, sir, can you hear me? Hello, sir, please unmute your mic. We cannot hear you.
Hello.
Yeah, now okay, right. Thank you, sir.
Since when it is being stopped?
Yeah, just 1 minute, I think 1 minute ago.
But I don't know how. Okay, sorry for that inconvenience.
Okay.
I had an impression that since 15 to 20 minutes, is it like that? Or no, right?
No, just 1 or 2
Okay,
minutes.
thank you.
Yeah.
I just have involved in completely presentation, so I could not see what is going on nearby. Okay, sorry for that. Okay, I just have to just understand that here you have radiating patch completely on the top plane, but here I have just considered a symmetry, means on the top plane, whatever I have in the ground plane also I have. In this case, I've just shown with 2 colors so that you can understand. Now you see clearly, this is the third step and this is the fifth step. So by looking at that, we should appreciate the technique, whatever we could achieve. Means technique we should appreciate, because if anybody make an attempt, then everybody will get that. So here the technique is successful. So by considering the symmetry on the ground plane, we should get radiation pattern in this direction that is possible towards. So that is how we had made another directional antenna for terahertz application. And then this is a little work we published in wireless network, because main problem in this, like this is since the work at 300 gigahertz. So we don't have any fabrication and testing facility. So that's why we could not make it in good articles. Okay, then later on to explore little about in the sense certain applications, what we did is like we had come up with we want to cover complete 360-degree rotation. Okay, so for that, like we had put antenna 1, 2, 3, 4, 5, 6 like this to realize, to cover complete azimuthal plane. My intention was to cover complete azimuthal plane, and then yes, S11 it agrees well, and then it is also having good isolation performance. That's okay. But mainly, I just want to show the radiation pattern. What we could able to achieve. It is able to give you this 360 degrees performance. but you will find certain nulls over here. There is null, null over here. Then in order to overcome that nulls, what we did is we just increased the number of elements. Okay, so now we had considered 12 elements. So this is also able to give me, and now if you look at, then somehow it is able to give us certain directional performance. So that is how this is one of the little application we just want to mention. So in this case, the point is like directional performance. Oh, okay. So next, I said just now one more work I'll be showing. So just it is yeah. Just give me 2 minutes. I thought of just downloading it, but I don't know. Suddenly I could not do it. So just I said like this is a work done in IEEE Access from our team. Since it's open access, I can download easily. Otherwise, I could have not done. Okay. Another we have done recently, like this is a publication in March 2023. It is not like, okay, it's okay, IEEE Access, but my intention is the technique what we have focused, that is important instead of a journal. So this is again at 300 gigahertz. Initially, okay, finally structure I'll show, then step-by-step process I'll just show that. Yeah, so here I'll just to show you the 2 steps. This is one structure. Initially, my structure was center feed, like you see here. If you look at this one, this is center feed, and as usual, if you look at this radiation pattern in D, then at the towards 90 degrees, I could not able to achieve it. Okay, so again, yes, same thing. What I did is that I just applied offset feed. Offset feed I applied, then you could see the result in the C pattern. Sorry, in C diagram. It is giving you almost directional pattern, but still I'm not happy with the directionality because I want exactly towards the 90 degrees. So in this case, what I did, I just had little bend on it. Means this is offset feed only, but little, I made it towards in another direction. So that was giving me directional performance. So this is how we explore the novel techniques, though it takes little time for us, but still we explore some novel techniques and our team, etc., etc. Again, we could not make it fabrication, but it is being made with conformal structure. If you look at C in the figure A and D, B, and then we too have also developed this lumped equivalent model. Nowadays, people are always asking in ResearchGate or in personal or in many places like how we obtain equivalent model. So no software is going to produce you equivalent model. Rather, you have to just approximate the pattern, sorry, the equivalent model using RLC structure. So you have to consider the combination of RLC element so that it will exactly fit to the antenna behavior. So now you can see in this diagram we had shown performance of conformal structure plus equivalent model in CST, HFSS, etc., etc. So somehow we managed to get directional performance. Again, this is also not fabricated because again the fabrication limits. And I think we have little 5 to 10 minutes time. I just have to show certain antennas where we had developed. In 5 minutes, I'll just conclude and then we'll have a question round if any questions are done. Here, I'm not going to discuss any theory. Theory in the sense concept and all. This is for cognitive radio applications, and I believe that people little knowing about cognitive radio. It is just what we call sense and use the frequency. Basically, cognitive radio means in the unlicensed spectrum or licensed spectrum, if anybody are using it, then you just don't use, you just look for another frequency. Simple. First, you look if anybody is using that frequency. If nobody are using it, then you can utilize it. Otherwise, if someone is using it, then you look for another frequency. That is what the cognitive radio technology. And from the literature, it is like clearly understood, like people are using ultra wideband because of its extensive advantages. Then we too have also explored that cognitive radio technology, and then where you require ultra wideband antennas and narrowband antennas. So what has happened? Like, let me just show you the literature. Literature has just presented this structure so far. Means, in fact, this is my little PhD work, I should say, but it is still considered to be novel techniques and all. Nowadays, it is like saturated, means the time has done. So many publications all been into the literature. So what I say, in this case, we require ultra wideband antennas and the narrowband antennas. So what researchers have done, they have inserted two antennas on a single substrate. If you look at this one and this one, there are two antennas. One is on the another side and another one is on opposite side. So this is on the top plane, both are in the top plane. And here, if you look at here, this is on the top plane, one structure, and this is on the ground plane. So this is ultra wideband antenna and this is narrowband antenna. And next, what other guys have done, then they have put ultra wideband antenna on one side, and on the beside to it, that is rotating. Like they use motor to rotate the orientation of your structure. And then like that, people have explored, and then they have put multiple antennas on a single substrate. So ultra wideband antenna, narrowband antenna, and other antennas are like this. And they have used reconfigurable mechanism, like they have used diodes, then maybe some other like pin diode or varactor diode or some other diodes which have been used to reconfigure the resonant frequency. Mainly reconfiguration takes place at frequency, but it is not like we can use reconfiguration for any mechanism also. But here they have used reconfiguration mechanism to shift the frequencies from one to another depending upon the available spectrum. Because just now I said, like if the spectrum is available, you utilize it. Otherwise, you have to look for, whenever you are getting a new resonant frequency, then your antenna has to operate at that frequency. So in that case, reconfiguration is used. So this is what the literature done. Then what we did is like some like again I said, like we'll think in different way. So they have done only one ultra wideband and one narrowband, and this substrate. What we had come up with is one ultra wideband antenna and then multiple narrowband antennas, like one narrowband, two narrowband, three narrowband, four narrowband, something like this. Okay, so in fact, it is nothing new, but for this application, we had adapted the combination of one ultra wideband antenna and multiple narrowband antennas instead of one ultra wideband, one narrowband. So just let me summarize the work. This is simple ultra wideband antenna which we have developed initially, and then this is 3-port structure. Means this is ultra wideband antenna, and this is one narrowband, and this is another second narrowband. So this is a fabricated structure, one narrowband, second. Later on, what we did is we have inserted two more narrowband. So this is my ultra wideband. This is one narrowband, second narrowband, third narrowband, and then fourth narrowband. So that is how we have inserted with the proper isolation. So again, techniques are very well known to us, like partial ground, then ground inserted, etc., etc. And then we also had a hardware in it. Means like we had little explored about hardware, where like we have used spectrum sensing and communication. Okay, because cognitive radio is all about spectrum sensing and communication. So we had used two antennas. One is for spectrum sensing and one is for communication. So then one antenna senses the spectrum, wherever the vacant hole you have, vacant hole in the sense vacant spectrum, at that case, like you will be communicating the signal. So you identify the frequency. If it is free, then you send a signal for the communication. So this is what the hardware we had developed. I could have discussed the design steps also, like I to have content further also, but because we are running short of time, so I think I should stop over here. It is almost 11:55, so we may have one or like questions for few much time. So then we have also developed equivalent models for all narrowband structures. Mainly, like we developed equivalent models for narrowbands only. For ultra wideband, it would be difficult for matching. So this is the complete work done during my PhD. So that is what the summary. And so with this, I'm just trying to stop here. If you have any questions, we can design techniques. Mainly, I am much interested in developing new techniques for, let's say, ultra wideband or directional performance, or maybe equivalent models or conformal structure. And then I said again, like we have the team who are working on different aspects like RF energy harvesting, absorbers, etc., etc. So that is again giving me a chance to explore new areas also. So far this is the work done by me and my team. And then in future we may be doing in some other interesting works to the community. So with this presentation, I would say that I'm just stopping the session. I would happy to take questions if you have, please. Any questions if you have, please?
Sir, if one to design any antenna, what is the reference value of the gain?
See, generally it depends upon the type of application you are using it, but mostly like 3 dB, 4 dB, or 5 dB, 6 dB. That is what expected. See.
Yes, sir. Because most of the papers mentioned that minimum 3 dB is requirement for the design.
No. See, let me tell you. See, until and unless you are going for a product, for example, I have certain requirement. Let's say for telemetry or whatever. In this case, I want directional performance with 20 dBi gain, because in academics, what we do mainly, like we design one particular antenna and then we'll just publication, we'll do publication and all. But the real utilization of that particular product comes in the implementation part. Like for particular application you are implementing means you will be getting your specification. So we too also had recently one consultancy work for satellite application. I just have to develop 2.45 gigahertz antenna, but it is having certain requirements like impedance bandwidth 2.41 to 2.48, then axial ratio below 3 dB for entire range 2.41 to 2.48. What people, if it is academic project and all, then what we do, once 2.45 we get axial ratio below 3 dB, then we'll be happy. But whenever you go to product or industry, then they want specification as per their requirement. And they also say that minimum 2 dBi in the complete range. We will not be happy. They will not be happy if you have less than 2 dBi in at least single frequency. I hope you got the point, Ram Prasad, right?
Yes, sir. And if we design an any antenna, yes, sir, I understand. If you design an antenna, sir, for example, it is radiating two frequencies. For example, 2.4, 3.4.
Right.
We consider at that particular frequency, we are considered a gain, right, sir?
Right.
For example, some of the paper mentioned a peak gain. I observed that paper which is not related to that particular frequency. The peak gain means not 2.4, not 3.5. Some other frequency they got, for example, 6.3. That peak gain they consider. Whether it is right or wrong, sir, in that paper.
No. See, the point is in the operating frequency. How do you decide operating frequency? wherever you have S11 below minus 10 dB, it is considered to be operating frequency, right?
Yes, sir. Yes.
So in that frequency range only, you have to specify the gain, because it is not utilized over the frequencies where you have not getting S11 in acceptable. So then why to mention that? See, that is what many of the times we should read the articles in good journals, published in good journals. Otherwise, then the persons who are just starting their career in this domain and all, they will be diverted. Diverted means they will be wrongly directed if you read such kind of articles. So better you read some good articles. And moreover, many of the times people present peak gain in case of ultra wideband, but not for multiband. In case of multiband, they may produce a resonant frequency at the again at different frequency. Otherwise, in that case also, if they produce peak gain, then the gain maximum they obtain at multiband. So that is the point one should understand.
I observed one IEEE paper also, sir. That's why I'm asking specifically.
So see, until and unless I see the paper, then I cannot comment roughly. And if possible, then you just share me the article, then I'll just tell that like what exactly the authors are intending.
Okay, sure, sir. Sure. Definitely.
Yes.
This is the last one more question regarding the gain and directivity.
Yes.
If compulsory directivity should be greater than gain.
See, the point is
yeah.
gain includes efficiency. Efficiency will not be more than 1, right? Then obviously directivity will be more than gain. Got it, right?
Yes, sir. Yes.
Simple. Gain won't be more than 1 because nobody is having efficiency than 100%. Yeah.
Okay,
Any more question? Yes, Ramprasad, please. Any more questions, please?
Sir, one request, sir.
Yes, madam, please.
To all the participants, please switch on your camera, turn on your camera, so that we can make a pic, one snap of the workshop, FDP. Sorry. Remaining. I request all of the participants, please turn on your camera. Yes. Thank you all. Now you can have a question and answer session continues with Anvis, sir. Please, you can clarify your doubts regarding the session.
Yes, please. If you have any questions, then I'm happy to answer them. And not only like questions, even I'm expecting some feedback from eminent professors, because I'm just 35, so I may be wrong at or maybe in wrong direction at some aspect. So it's not always like asking questions. So if like from senior professors, experts and all, I would humbly request your suggestions or improvements or any other things. Because I should not say that questions only. Because in the video I could see like great professors and all. Please. Okay.
Dear participants, please, if you have any questions or any doubts, you can express.
Hello, sir.
Yes, please.
We are using in so many applications MIMO antennas.
Right.
Now, why that is MIMO antennas are so popular? Any characteristics, sir? Any
See,
characteristics of
mainly whenever you talk about MIMO antenna, then the first question like throughput, you just increase the throughput. Then there are like, no, I simply say if one person is shouting, then multiple persons are shouting same content. That is as simple as that technology. So if one is transmitting, then what is the effect? And then if at a time multiple guys are sending a signal, then it would increase your throughput, and then that is a mainly a thing. And then data rate also it will increase. So that's why we'll go for MIMO.
so characteristics also we are applying many antennas, sir.
Oh,
So
what do you mean by characteristics?
What are the characteristics of MIMO antennas, sir?
Acha. So you, for example, like you want mainly a radiation pattern should not be disturbed. And another thing is like you should have proper isolation between the elements. And then it needs to be compact size also. It is not like we are using multiple antennas. Then in that case, antenna size is what increased. That is also needs to be considered. Isolation also needs to be considered. And then other parameters like ECC, TARC, MEG, then CCL, all those things needs to be considered for MIMO case.
Performance parameters also is good, sir. So, sir.
Yes.
Okay.
Yes.
Okay, sir. Thank you, sir.
Good afternoon, sir. Myself, Sri Babu.
Yes, please.
Sir, I'm working on a MIMO antenna.
Okay.
But already one design is completed for the 4-port MIMO antenna 2x2 configuration.
Okay.
But just I'm working on that sub 6 GHz only. But I want to integrating on sub 6 GHz and millimeter wave frequencies.
Okay.
Can you suggest me which type of antenna is good for the both antenna can be radiated? I mean,
See,
tuning of both.
sub 6 gigahertz means somewhere else in 3.4, 3.5,
Yes, sir.
3.6.
N78 band, sir. Myself N78
And then
band.
you said
3.3 to
millimeter
4.3.
wave. What is like which frequency you are considering in millimeter?
It's
28,
the
34,
tuning of 20 gigahertz, sir.
20 gigahertz,
26.
but 26, right?
Yes.
See, in this case, see, antenna always produces higher order modes. So
Yes,
if you are start simulating a structure from, let's say, 2 gigahertz to 20 gigahertz, then in between you'll find multiple resonance frequencies. Not exactly resonance, you'll find the higher order modes, let's say 8, 9, 10, like this. So it is very difficult for you to come up with that structure. Rather, what you do, you just take two antennas on a single substrate, one for this sub 6 gigahertz and another one is on the 26 gigahertz. That would be better with proper isolation, because antenna would be completely independent because you are maintaining isolation, and then you won't find any other higher order modes. And moreover, the size would be maintained in the same size only.
Yes, sir.
Okay.
Yes, sir. That means you are saying about the integrated method. I mean, hybrid method.
Yes. Don't take a single element which works at sub 6 gigahertz and 20, because it is very difficult for you to prove in a paper or wherever, because multiple harmonics and all like higher order modes you will get. Rather, you have two different antennas. One is at sub 6 and then one is at 26. That would be better.
So definitely. Yes, sir. I'm concerned about your concerns.
Yes.
Sir, one more thing, sir.
Yes, please.
Sir, while you are considering about that envelope correlation coefficient, that is a similarity of radiation pattern, right?
ECC.
Yes, sir, ECC. The ECC can be calculated by using S parameters and as usual as radiation pattern.
Right.
So the most of papers, the radiation pattern you are considering that by using of the MATLAB code, you have to dump that the same S parameters, then you can calculate the procedure.
Correct.
Sir, if you don't mind that, because of I'm the beginning of this my maintenance designing, can you share that code, how to write that MATLAB code for
See,
CCL and
as of
ECC?
so far, what we have explored is using S parameters only. Many less
Yes, sir.
times people ask from radiation pattern, because see,
Yes, sir.
there would be a difference. But nobody that much stressed like I want only radiation pattern, ECC only, or S parameter only. People are accepting because we too published many articles in Memo, and then
Yes, sir.
very less times we get this question of a radiation pattern based upon ECC based upon this thing.
But as sir, I already published one. I mean, I communicated in AU journal, but I got the one comment from that reviewer. That is very particular to mention how we can be implementing the radiation pattern through MATLAB. Can you share the code? That's
I
what
have
I'm
to get it actually. In fact, I said I just tried with only S parameters.
Yes,
So from there, I'll just try from my sources. Then I'll get you if possible.
Yes, yes. Yes, sir, already as parameter point of view, I write that code and I send that by using of the radiation pattern from my antenna. R 2020 version is there. I can go for the far field, MIMO. I can get that radiation, far field radiation. But he's asking about radiation pattern. That enter the radiation pattern in the band is good or not. He can asking the same thing, same question also, sir. But exactly,
Okay.
I can't get that. What is he as asking me?
What you do, please ping me the question to me in personal. Like you take,
Yeah, sure, definitely.
I have mentioned
Definitely.
my mail ID.
Yes.
Then better you just contact
Yes, sir.
me in person because it's taking. Yes, please.
Yes, sir. Sure.
Any more
Hello?
questions? Yeah,
Thank you, sir. Thank you for your support. Thank you.
yeah, sure. I'm happy to answer that. Any more questions, please? If anyone is having any more questions. So I think we can wind up if there are no more questions.
Sir, yes, sir.
So I'll just sharing my contact here, email ID and phone number. If you have just any questions or for collaboration, and we are always ready. So please contact us so that we can improve our network, so that we'll produce some good content to the community.
Okay, sir. Sure, sir. Thank you, sir. Thank you so much for your support.
So I should say thank you for the invitation to the convener and then patrons, chief patrons, and then coordinators of this FDP, 5 days FDP. It would be good to the researchers to learn extra. Thank you one and all.
Sir, your presentation is completely new and more informative, sir. And it is thought-provoking for new researchers. You discussed and shared your work also, which is more valuable, and it might be a trigger to young researchers in the field of antennas. Thank you so much for your presentation and interaction. Thank you, sir. Thank you once again. Thank you one and all. We'll meet again tomorrow at 10 o'clock for next session. Thank you.
Thank you all.
Can I leave, ma'am?
Yes, sir. Everyone can leave now.